Hey, welcome to the video. In this video, we'll be going through partial derivatives, and specifically, we'll be going through two examples that demonstrate partial derivatives. So, to begin with, I want to explain that partial derivatives are used when you have multivariables in a function, like you have f of x, y, or f of x, y, z, or f of z, y, anything like that. And what partial derivatives are essentially is that you are deriving for each variable and treating the variable that is not in focus as a constant. So say you had f of xy, you'd get f of x and you'd get f of y. Here you'd be treating y as a constant, and here you'll be treating x as a constant. And then these two derivatives that we found are our partial derivatives. So yeah, let's get into some examples. Let's see if it makes sense. First example is y equals to ln x plus t squared. So we're told to find the partial derivatives of this equation. First thing, you want to identify the variables. So your variables here are x and t. So y can be seen as a function of x and t, and that function is ln x plus t squared. So the first partial derivative I want to get is f of x, which is, since x is our focus of the derivative, we would apply chain rule to get this. So this will end up being 1 over x plus t squared multiplied by 1, because the derivative of x is 1. If you don't know your derivative rules by now, you should go back to the previous videos and check them out. So this one simply f of x is equal to 1 over x plus t squared. Now we also need to get f of the second variable, f of t, and that would be equal to d dt of ln x plus 2 plus t squared, sorry. And now t is the focus of this derivative, so again we need to apply the chain rule here because we have our inner function within the outer function. So again it's 1 over x plus t squared, but this time it's multiplied by the derivative of t squared, which is just 2t. So our final answer for ft is 2t over x plus t squared. Yeah. So that f of x here and f of t there is our partial derivatives for that equation. So let's try another equation. Let's try fxyz equal to xy squared times e minus xz. So we're told to find the partial derivatives of this function, and we have 3 variables here instead of 2. So what do? We do the same thing we did last time. We find the derivative of x. Instead here we're treating y and z as a constant, and find the derivative of y, treating x and z as a constant, and then find the derivative of z and treat x and y as a constant. So we'll have 3 partial derivatives. So starting off with fx, that's ddx x y squared e minus xz. Yeah, if I made any mistakes, please let me know in the comments. But the overall answer for this one can be multiplied throughout, or simply we can take out e minus xz out of the equation, which I think is a better option, minus xz, and that will end up with this, which is 1 since e minus xz is taken out, and end up with these two, so minus xz, and that is our partial derivative of x. Go on to the partial derivative of y. Same thing, ddx of x y squared e minus xz, and we treat here x and z as a constant. So this should have been dy. Final answer would just be 2xy e to the minus xz. That's a partial derivative for fy. Since I'm running out of space, let me use the second page to find the derivative of fz. Again, it's just dz this time, of xy squared e minus xz. And now z is the focus of the derivative, so that's treated as a constant, x y squared, and we find the derivative in terms of z of e to the minus xz. And that leaves us with minus x squared y squared e minus x z as our partial derivative of z. And this value here is our final partial derivative. I just noticed that I forgot to put a squared here when we're finding the partial derivative of x. It should be y squared e minus xz, and in brackets y minus xz. Bye.